Hello everyone, and thank you for joining today. For years, we have lived in an era of hydrogen hype, a time filled with glossy brochures and ambitious press releases about a clean energy future. But for most of the world, that future has remained just out of reach. Today, we are here to talk about a game changer. We are looking at the NEOM Green Hydrogen project in Oxagon, Saudi Arabia. The headline here isn't just another plan. The headline is that they actually built it. As we dive into this investigation, I want you to look at the sheer scale of the facility behind me. This isn't a pilot plant or a laboratory experiment. This is the world's first truly industrial-scale green hydrogen ecosystem. Today, we'll explore how they turned a desert vision into a massive infrastructure reality, and why this project succeeded where so many others have unfortunately failed. Before we look at the success of NEOM, we have to confront the uncomfortable hydrogen reality. If you follow energy news, you've seen hundreds of gigawatts of capacity being announced across every continent. However, the hard truth is that only a tiny fraction of these projects ever reach steel in the ground. The gap between ambition and execution is enormous. In just the 12 months leading to the end of 2025, approximately 4.9 million tons per year of announced low-emission capacity was withdrawn globally. In the European Union, a staggering 20% of projects have been shelved, scaled back, or significantly delayed according to Westwood analysis. The world is full of announcements, but building these projects requires overcoming massive financial and logistical hurdles that most developers simply aren't ready for yet. NEOM is the exception to this global trend, and today we will uncover why. Our story takes place at 28 degrees north and 35 degrees east, on the Red Sea coast of Saudi Arabia. This is Oxagon, a key node in the NEOM development. It is a place characterized by turquoise waters and vast sun-drenched sands. But don't let the beautiful scenery fool you. This is an industrial frontier. On this coastline, something happened that has not happened almost anywhere else on Earth. The project actually got built. While other developers were stuck in regulatory loops or waiting for subsidies that never came, the teams here were moving earth and pouring concrete. The geography of this location is not accidental. It is a strategic choice that combines natural resource wealth with access to global shipping lanes. It is the perfect stage for the world's most ambitious energy experiment to transition into a working reality. Let's talk about what industrial scale really looks like. We aren't talking about a few solar panels in a small tank. We are talking about 2.2 gigawatts of electrolysis capacity. To power this, the project utilizes approximately 4 gigawatts of combined solar, wind, and energy storage. The physical footprint is staggering. There are 257 massive wind turbines and a solar farm that is roughly the size of Manhattan. All of this is connected by a dedicated 4 gigawatt transmission grid built specifically for this site. The goal? To produce 600 tons of green hydrogen every single day, which will then be converted into 1.2 million tons of green ammonia every year. It's important to note that while the steel is in the ground and the design is set, full-scale production is the next great milestone. This is a massive renewable energy machine, designed to process nature's elements into a tradable global commodity. Building something this big requires more than just engineering. It requires a unique financial and political structure. The project is built on a foundation of 3 owners, 1 balance sheet. This is an equal joint venture known as the NEOM Green Hydrogen Company. You have NEOM providing the land, the infrastructure, and the immense political commitment of the kingdom. You have ACW Power, a giant in renewable energy development and utility-scale delivery. And finally, you have Air Products, acting as the primary EPC contractor, the system integrator, and the exclusive off-taker. This partnership wasn't just about sharing costs, it was about sharing expertise. Together, they secured $8.4 billion in total investment, including $6.1 billion in non-recourse financing from a consortium of 23 international banks and institutions. This level of financial backing from the private sector is a massive vote of confidence in the project's viability. A question I often hear is, why Saudi Arabia? Can an oil-exporting giant really become a leader in green hydrogen? The answer lies in their natural and strategic advantages. First, they have some of the world's strongest desert irradiance for solar. Second, they have coastal wind resources that often peak when the sun goes down, providing a natural balance. Third, they have vast, empty terrain at a scale few countries can offer. But it's not just about the weather. Saudi Arabia has export DNA. For decades, they have mastered the art of moving energy to global customers. With the Red Sea shipping lanes on their doorstep and the state-level intent of Vision 2030, the country is leveraging its history as a hydrocarbon leader to diversify into the molecules of the future. They aren't just changing their energy source. They are evolving their entire economic identity for a post-carbon world. Now, let's look at the business model, because this is where many projects fail. In the world of green hydrogen, making the molecule was never actually the hard part. The chemistry is well understood. The real challenge is selling it, delivering it, and financing it. The NEOM project realized early on that the product isn't just hydrogen, It's a reliable supply that a customer can actually use. By taking sun and wind, turning it into electricity, then hydrogen, and finally ammonia, they created a product that can be shipped across the ocean. The brilliance of this model is the 30-year contract. They didn't build this plant, hoping someone would buy the hydrogen on a whim. They built it against a 3-decade commitment that ensures a steady route to global markets. In this industry, a signed contract is just as important as a working electrolyzer. For the technical minds in the room, let's briefly touch on how it actually works. The core process is simple electrolysis. H2O becomes H2 and O2. Renewable electricity from the wind and solar farms enters the electrolyzer units. Under this electrical load, water molecules are split apart. The hydrogen is captured for processing, while oxygen is produced as a clean co-product. The NEOM Green Hydrogen company is utilizing advanced electrolysis technology from ThyssenKrupp. Additionally, they use air separation units to extract nitrogen from the atmosphere. This nitrogen is then combined with the captured hydrogen to synthesize ammonia. It is an elegant, closed-loop process that uses nothing but water and air as inputs, powered entirely by the natural forces of the sun and the wind. However, there is a fundamental tension at the heart of this project. Electrolyzers are expensive pieces of industrial equipment that reward steady, high utilization rates. They want to be running all the time. But renewable energy, the sun and the wind, does the exact opposite. It varies by the hour, by the day, and by the season. This tension sits at the center of every green hydrogen project on Earth. How do you keep a giant, multi-billion-dollar plant busy enough to be profitable when your fuel source is intermittent? At NEOM, the solution was to go big on both solar and wind generation, totaling about 4 gigawatts, and tying them together on a dedicated grid. The goal was to create a renewable energy machine that could provide a more consistent flow of power to the electrolyzers than either source could provide on its own. This brings us to why the hybrid model matters so much. You see, the sun and the wind operate on 2 different clocks. As you can see in this illustrative chart, solar power peaks at midday, creating a massive surge of energy. Coastal wind, however, often runs strongest during the evening and throughout the night. By pairing these 2 resource profiles on a single site, they overlap less and cover far more hours of the day than solar or wind could ever do alone. This hybrid supply is not just a feature, it is central to the entire design of the plant. By maximizing the hours the electrolyzers are running, they significantly lower the cost of every kilogram of hydrogen produced. Of course, the exact utilization rate they achieve will only be known once we see the real-world operating data, but the design logic here is absolutely sound. Another frequent question is, where does the water come from in a desert? It's a valid concern. You can't have a hydrogen plant without a massive supply of water. The solution at NEOM is the Red Sea. They take seawater, put it through a desalination process, and then further purify it to create the processed water required for electrolysis. Now, desalination does add extra plant costs, energy requirements, and brine handling obligations. But here is the secret of hydrogen economics. For a project of this scale, the cost of raw water is rarely what decides the final price. It is the cost of electricity that truly moves the needle. By securing ultra-cheap renewable power, the team can afford the energy penalty of desalination while still keeping the overall project competitive. It is also critical to understand that hydrogen is only step 1. For this project, hydrogen is not the final product that leaves the port. Once the hydrogen leaves the electrolyzer and the air separation unit extracts nitrogen, they enter a synthesis loop. This process combines them into ammonia. Why do this? Because while hydrogen is the energy carrier we want, it is notoriously difficult to move. By converting it into green ammonia, the project creates a stable, liquid product. The goal is to produce up to 1.2 million tons of this green ammonia every year once the plant reaches full operation. This conversion is the bridge between the production site in the Saudi desert and the industrial customers located thousands of miles away in Europe and Asia. So, why go through the extra step and expense of converting to ammonia? The answer is simple. Because the world already knows how to move ammonia. If you want to ship liquid hydrogen, you have to cool it to a cryogenic -253 degrees Celsius. That requires incredibly specialized vessels, expensive terminals, and you deal with constant boil-off losses during transit. The infrastructure for this simply doesn't exist at scale. Ammonia, on the other hand, is liquid at a much more manageable -33 degrees. We have decades of experience with ammonia tankers and port practices. There is already an established global trade for it, and it is a valuable commodity in its own right for fertilizers and chemicals. By choosing ammonia, NEOM plugged into a global logistics network that was already ready to receive their product. This brings us to the offtake advantage. I cannot stress this enough. A hydrogen plant without customers is just an expensive science project, not a business. The NEOM project succeeded because it secured a 30-year exclusive offtake agreement covering every single drop of green ammonia produced. Air Products, as the sole offtaker, has even signed marketing agreements with partners like Yara to ensure the volumes find a home. Why does this matter? Because bankers do not lend billions of dollars against ambition or good intentions. They lend against contracted revenue. This signed, long-dated route to market is exactly what turned a bold announcement into a financeable project. It provided the security needed to raise $6.1 billion in debt, proving that the market for green molecules is real if you can guarantee the supply. Let's compare NEOM to the projects that stalled. Around 60 major green hydrogen projects were cancelled in 2025 alone, and almost none of them failed because of the chemistry. They failed because they lacked the system approach we see at NEOM. While NEOM had exceptional co-located solar and wind, stalled projects often relied on expensive or grid-dependent electricity. While NEOM built its own port and transmission links, others were missing key infrastructure. Most importantly, while NEOM had a 30-year contracted offtake, many other projects were waiting for subsidies or navigating shifting regulatory definitions without a committed customer. NEOM closed its $8.4 billion financing before construction risk even began, whereas others repeatedly deferred their final investment decisions until it was too late. The difference wasn't the technology, it was the alignment of every single piece of the puzzle from day one. Now, we must be realistic. Construction is nearing final completion, and commissioning has started with the first energization. That is a massive, genuine achievement that proves the project can be built. But, as any engineer will tell you, this is also where the hard part truly begins. Built does not mean proven. The next phase is about demonstrating that this massive system can actually operate as intended. We are now entering the period where commissioning, reliability, utilization rates, and product quality must all be proven in real-world conditions. The logistics of moving 1.2 million tons of ammonia and the final delivered cost are still questions that only operation can answer. The industry is watching closely because the transition from a construction site to a functioning factory is the ultimate test. The commissioning test is essentially a question of integration. Can thousands of individual components behave as one single system? The team must now prove that the electrolyzers can operate across varying load ranges as the wind and sun fluctuate. They must integrate that power with a variable grid without crashing the system. They have to ensure that the hydrogen handling and safety systems are foolproof at an unprecedented scale. They need to maintain stability in the ammonia synthesis loop, which traditionally prefers a constant feed. With solar and wind scheduled for completion by mid-2026 and the first product expected in 2027, the focus shifts to ramp up reliability over months and years, not just days. This is where the theoretical designs meet the messy reality of industrial physics. We also have to talk about the electricity cost test. There is a common misconception that just because a plant is big, it must be cheap. In the world of green hydrogen, electricity is the largest single variable in the economics. A massive plant does not automatically produce cheap hydrogen. To get the price down, you need a combination of two things that rarely arrive together: very inexpensive power and very high equipment utilization. If your power is cheap but you only run the plant 30% of the time, your capital costs will kill your margins. If you run 90% of the time but use expensive grid power, your operating costs will be too high. NEOM's success depends on how well they have balanced these two levers. While this chart shows general industry weightings, it highlights the challenge every developer faces in this new economy. This brings us to the utilization trap. An idle electrolyzer still costs you exactly the same in terms of interest payments and depreciation. As you can see, when you have high utilization, you spread that massive capital cost across far more tons of hydrogen, and the unit cost falls. But with low utilization, the same capital is spread across fewer tons, and your unit cost climbs sharply. This is exactly why the hybrid renewable supply and storage were designed into the NEOM project from the very beginning. They aren't just trying to produce green hydrogen, they are trying to produce the cheapest possible green hydrogen by maximizing every hour of the day. Real operating hours, not just the nameplate capacity of the machines, will ultimately decide if NEOM's hydrogen is a commercial success or an expensive lesson. Even if the costs are optimized, we have to ask, will customers actually pay the premium? Renewable ammonia is not competing against a vacuum. It is competing against conventional ammonia made from natural gas. Conventional ammonia is produced at an enormous scale with a well-understood price. For NEOM to thrive, it must find buyers who are required by law, or willing by choice, to pay more for the carbon difference. Potential markets include fertilizers, which is the largest existing market, and emerging sectors like shipping fuel, which depends on new engine technologies and environmental rules. There is also potential for industrial feedstocks in chemicals and refining, or even cracking the ammonia back into hydrogen for imports. But remember, in this business, only contracted volumes count as committed demand. The market's willingness to pay the green premium is the final hurdle. We must also remember that the produced cost is not the delivered cost. A customer in Rotterdam or Yokohama doesn't care how cheap the hydrogen was at the electrolyzer in Saudi Arabia. They care what it costs when it reaches their facility. Every single link in the chain, from the plant to storage to the port onto the ship through the receiving terminal and finally to the customer, Its cost consumes energy and results in some product loss. This logistical tail is significant. For green hydrogen to truly replace fossil fuels, we have to optimize the entire journey, not just the production site. NEOM's proximity to the Red Sea shipping lanes is a huge advantage, but the efficiency of that global supply chain will be a critical factor in the final price tag for the end user. Looking forward, we have to ask, can this model be copied? Other regions are trying. Namibia has the Hyphen project, a $10 billion program. Australia has several export schemes, though some have been cut back recently. Chile has world-class wind, but is very far from major markets. Oman is building the DOEM hub, and North Africa has the advantage of being close to European demand. But while resources like sun and wind can be found elsewhere, the other parts of the NEOM model are much harder to replicate. The combination of massive scale, multi-billion-dollar financing, guaranteed offtake, integrated infrastructure, and absolute political commitment is a rare alignment. These soft factors are what NEOM actually assembled, and they are what other nations will struggle to match in the coming decade. If there is one real lesson from the NEOM investigation, it is this: hydrogen is a system, not just a technology. The hardest problem at NEOM was never the electrolyzer itself. It was the immense complexity of making everything arrive at the same place at the same time. You need the renewables, the water, the electrolysis, and the ammonia synthesis all working in harmony. Then you need the port infrastructure, the massive financing, and the committed customers all aligned. If any one of these 7 pillars is missing, the whole project collapses. NEOM's achievement isn't just a technical one. It is an organizational and financial one. They managed to build a complete ecosystem from scratch in the desert, proving that the system approach is the only way to make the green hydrogen economy a reality. So, what is the ReneEnergy verdict? Is it built? Yes, absolutely. Is it proven? Not yet. NEOM has shown the world that a multi-gigawatt green hydrogen project can move from a bold announcement to physical infrastructure. That alignment of resources, partners, and offtake is the true achievement here, not just the chemistry. However, we must be clear, construction does not prove commercial success. The decisive evidence is still ahead of us. We need to see operational reliability over years. We need to see sustained electrolyzer utilization. We need audited production figures and delivered ammonia costs that actually make sense for the market. We need to see if customers come back for more. The project has cleared the first hurdle, but the marathon of real-world operation is just beginning. As we conclude, we must ask, if NEOM works, what changes next? The green hydrogen industry has reached a turning point where it no longer needs more announcements or more paper projects. What it needs are operating projects that demonstrate real production, real customers, and economics that can eventually survive without permanent support. NEOM is the first to step into that spotlight. If they succeed, they will provide the blueprint for a global energy transition. If they struggle, they will provide the warnings that the rest of the industry needs to hear. Either way, the work being done at Oxagon will shape the energy landscape for decades to come. Thank you for your time, and I look forward to seeing how this investigation continues as the first molecules begin to flow in 2027.